Hello, everybody. This is the last lecture of this semester. So, in this lecture, I'll cover the several examples using some energy approach in order to get PCR. Let's go through. If you remember, in last lecture, I covered one example of cantilever column. At that example 1, we have somewhat considerable error. So in this example 2, I'd like to solve the same problem but somewhat different way. So in example 1, when I calculate this strain energy, I used curvature, moment equal EI curvature. In example 1, we calculate curvature, right? From this one, then 2A. So we input here, and then moment square. So basically, we use curvature value. So in that some procedure, the curvature is constant along this length. So it is not real. So we have somewhat big error. In this approach, I will directly use displacement input in calculation U. Let's look at this one. This P here and delta. If we take out this part, the lateral displacement is V, right? So this displacement is delta minus V, right? So we can calculate internal moment here. How to calculate? P times delta minus V, like that. Yeah, firstly, we assume the same displacement, the equation, as example 1. So the moment can be calculated like this. Delta equal AL square, right? If we assume the displacement equation like that. So this delta AL square you input like that. This V AX square like that. Okay, this is a moment. So strain energy equation is this one, right? 1 over 2 integration moment square EI dx. At this moment you input this value here. Okay, PA L square minus X square square. Then if you calculate this equation, you get this value. So the difference between example 1 and example 2. In example 1, curvature value input. Example 2, displacement is input directly. That is different. Strain energy, so total energy is this strain energy. Potential energy is identical as example 1. And then take a derivative regarding A. Then this equation is equal to 0. So PCR equal 2.5 EI over L square from this equation. So exact PCR is this one. So we have 1.2% error. Very close. If we consider the situation here, this is the exact curve. Assumed curve is somewhat dot line like that, but they are very close. So we have a very close equation. And another thing is that in Rayleigh method provide always upper bound solution because this displacement assumption AX square we assume like that is mathematically constrained from nature shape. Do you understand? Nature shape is this solid line, but we assume our displacement. In order to make this displacement, there must be some constraint. The meaning we assume this dot line, then we make some unnecessary constraint. So we provide unnecessary constraint. That means stiffness increase effect. Mathematically constrained cause stiffness increase effect. That's the Rayleigh method provide always upper bound solution. Let's look at the example 3. In this approach, we assume some displacement shape is A1 x squared plus A2 x cubed, like that. So in this assumption, we use two terms, A1 and A2, in order to make some real displacement. If we use higher order term, we can consider more real displacement, like that. So we take a derivative like that, second derivative like that. Yeah. So total energy is strain energy plus potential energy. Strain energy can be written like this. Potential energy can be written like this. It is a very standard equation. You need memory. This standard equation. As long as you know this equation, you assume some displacement shape like that. So you take a second derivative value here. You take one derivative here. That's it. And then integration. Then you can get the solution. In example number 1, we input this curvature value. It shows very big the error. In this example, we still use this curvature term, but we assume deflection is a very high order term like that. Then we can get a very exact result. That's the procedure. You input V2 prime value here, V1 prime value here. Okay, that is the equation. Then you calculate this integration, and then you take partial derivative regarding a1 and a2. You have two, a1, a2. So partial derivative against a1. Then you get this equation. After integration, this one. And then partial derivative against a2. Then you get this equation. The equations become somewhat longer. So we use lambda equation. We let lambda equal PL square EI from this one. Then this equation can be written this matrix form regarding A1 and A2. A1 and A2. You can write this matrix form, right? If you let this lambda. This is the equation. So in order to satisfy 0 in the right hand side, this determinant must be 0. Right? We have the similar experience in previous chapter. The determinant must be 0. So from this equation, you get this resulting equation. And then from this on, your lambda value equal 2.49. Your lambda is this one. So this is 2.49. So your PCR equal 2.49 EI over L square. If you compare to the exact solution, it shows 0.81% error. You get some better result. Let's go to example 4. In this example, also cantilever column. Different thing is that you have force at the top and at the mid height. Firstly, you have to assume deformation shape, right? So in this equation, you assume the displacement shape using cosine a1 minus cosine pi x 2l. After assume this displacement equation, you have to check the boundary. That means this equation whether satisfy the boundary or not. Let's check from this equation. V0, this point, right? Displacement at this point equal 0. Let's input 0 instead of x0 here. Then cosine 0, right? Cosine 0 is 1. 1 minus 1. So v equal 0. Satisfy. And VL equal A. VL, this point. If you input L here, then LL. Cosine pi over 2. What is that? Equal 0, right? So V equal A. Yeah, this A. That means this A. So how about slope at the bottom? Equal 0. So if you take a derivative here, then pi 2L, move here. So x equal 0, sine 0. Sine 0 equal 0. V prime 0 equal 0. That means slope equal 0. So we can check the boundary condition satisfied. And then we take second derivative, this value. And then it is simple. You calculate U, strain energy. Strain energy equation is this one. It is standard value. V2 prime, so we can use this value. So input this one and integration, then you get this value. How about potential energy? Equation is this one. In potential energy, you must be careful. If you see here, in potential energy, we have to do integration. But from here to here, what is axial force? This range. What is axial force? This P and this P applied. The reaction is 2P. In this range, 2P applied, right? from mid height to the top, the axial force is P, right? This P. Is it correct? So we have to divide into two integration. You see here, V equal from 0 to L over 2, this range. Your P equal 2P, V prime square dx, minus from L over 2 to top, this range, your P equal P, V prime square dx. Your V prime value is this one. You input this one here and take integration. Then you will get this value. And then you get the strain energy and potential energy. If you add together, you can get the total energy. You can take derivative equal to 0 from this equation, derivative this one equal to 0. Then you get PCR, pi cube 2, 3 pi over 2, like that. That is 2.09 EI over L squared, okay? If you use some differential equation, you can get the exact result. That is 2.067. As you see, they are very close. The error is 1.1% error. So although you input the curvature value here, your assumed equation is cosine equation. Then after you take the second derivative, your equation, curvature equation is not constant value, is not linear value. So it gives us a very accurate solution. Let's go to final example. Yeah, it is at the bottom hinge, at the top roller. We have the axial force P at the top and mid height also. So we have to assume this deformation shape, this diffraction shape. V equal A sine pi x over L. To check the boundary condition first, right? At the boundary, displacement at the bottom equal 0. So if we input here x equals 0, sine 0, then v0, right? And then how about at the top, x equals L? If we input here, then sine pi equals 0 again. Displacement is 0, right? So boundary check. Displacement is satisfied, and then you can calculate v prime, v2 prime. v2 prime 0. What does that mean? v2 prime means the moment. 0 means moment at the base equal 0. Why? It is a hinge. So if you input 0 instead of x, sine 0, 0. Okay, it is satisfied. How about the moment equal at the top? Equal 0, because it is a hinge support. So v2 prime L must be 0. v2 prime L here, sine pi equals 0, so it's 0. So boundary check is satisfied. So we can calculate U equal 1 over 2, that is standard equation. If we input this v2 prime here, then you can get this equation. If you take the integration, you can get this value. How about the potential energy? What is the actual force in this range? You have P at the top, P here, so it is 2P, right? This range, your actual force is P. So you have to divide into two integration. In this range, your P equal 2P, and the integration, this range, your P equal P, L over 2L. If we input this value here and here, you can do integration like that. This one, ultimately you get this one. This is strain energy, this is potential energy. Add together is total energy. Take a derivative against A, then you can get this equation is equal to 0. From this equation you can get PCR, right? PCR equal this value. Now we have to finish the lecture. Thanks you for your attending my lecture and then also your hard work. God bless you. Bye, everybody.